Hey everybody, welcome to Verizon. Thank you for being here tonight. My name is Miguel Alvarado. I am Director of Analytics for a group called OnQ here at Verizon. Unfortunately, we can't tell you a lot of what we're doing right now because we haven't launched, but one of these days we'll be able to. I want to make a couple announcements. So as you know, Databricks is here. So if you want to talk to Databricks, you saw the lady that you have to talk to. Mesosphere is here. So back there's one of them. Over here's the other guy. So if you guys have any Mesos questions, comments, or any conversations that you want to have with these guys after the sessions, feel free to reach out to them. Also, we're always hiring, of course. So there's a hiring booth over there to the right. So if you're interested, you can go talk to our recruiters. I'm going to pass it on to Hai, who is part of our big data team over in Palo Alto. Oh, yes. One more thing. The most important thing that I'm supposed to talk about. So we are doing a raffle, and we're giving away awesome prizes. So we have an Apple Watch, we have 2 Apple TVs, and we have 2 remote control drones. So if you want to participate in the raffle, make sure that your contact information is captured in those iPads that you will find in the recruiting booths. So those are fun prizes. Make sure that you participate in the raffle. So now I'm really going to pass it on to Hai, who is part of our Palo Alto big data team.
Thank you, Miguel. So thank you for the goodies, and I hope everybody's going to stay till the end of the talks. But also hopefully all the talks going to be valuable and interesting to you. And also I'd like to call out Joey. Joey is taking the picture. But thanks. So big thanks to Joey for doing a great job on planning and coordinating the event and make all these happen. So my name is Hai Xiao. I'm with the Big Data Analytics Group of Verizon Labs. We are located in Palo Alto, a little bit north from here. And we have grown from 1 to 70 people in the last 2.5 years. So we are still growing. And you can see we are a group of fun-loving people. And we all love working with data, and that's why we all joined the group. And we also have pretty nice hardware here. So we have a cluster of 240 node production cluster, and we also have a 100 node cluster for development and testing. And all those nodes are running Spark. And we also have a lot of interesting data from many different domains like advertising, cybersecurity, Internet of Things. And currently we are processing over 30 billion records per day, and the volume of data is still growing. And today we are going to have, we're going to cover the first half an hour with 2 talks from the team. So one from Mike on data processing, and the second one will be by Deb, Pramod, and Dibendu on some of the results and examples from running some of the machine learning algorithms. So without further ado, I'd like to pass it to Mike Quinlan from the platform team of Big Data Analytics.
Thanks, Hai. So I'm going to talk about an application that we wrote to do some data ingestion for the multi-tenant cluster that he just introduced to you. I'm going to talk about writing basically a Spark driver that has reliable error handling. It's multi-threaded, and some hints on performing graceful shutdowns. So this is our use case. We currently ingest greater than 10,000 files a day, with a total daily volume of 6 terabytes uncompressed. This is roughly 12 billion records. And this requires an ingestion application that has long uptime. It's multi-threaded, so they can process all these files. And I'll also give you a hint about some controlled shutdowns for maintenance. So basically, the purpose of my talk is to share some secrets about writing a good Spark driver, one that's stable and is easy to deploy. So I'm going to give you a simplified application architecture, just show you the inputs and outputs. And then I'm going to give you coding patterns for error handling, multi-threaded drivers, and graceful shutdowns. Taking questions at the end, I'm told, of everybody's talk. So here's a simplified application architecture. We've got an event queue. It's currently using Apache Kafka, but you could use anything like RabbitMQ. And the purpose of this is to store events that tell us some metadata about a file that exists on one of our landing servers. So in this case, I'm giving a very simple input, which is just a JSON with the file name. The distributed file system is where the clients send us data. And it's a GlusterFS, but that's not really important for this talk. So the rest of the talk is going to concentrate on this gateway node, which is running a Spark driver instance. And this driver instance is going to perform a very simple map, let's say map operation on the data. So there's input, map, and then save to HDFS, which is saved to the local disks in the Yarn containers, those running Yarn containers. Okay, so here's the application skeleton. I'm going to progressively go through this, and hopefully you can watch the video to get the details of the code. What we've done is we've mimicked a Spark streaming microbatch. The reason for this is that we don't have a very strict SLA. We don't need to have the data right now through Kafka. Again, only the metadata is going through Kafka. And this gives us a little bit more control than Spark streaming. We can, and I'll go into that a little bit. Essentially, initialize the Spark context. We create a thread pool of some size, maybe like 15 to, I don't know, 100. And that thread pool threads on that thread pool will process files, individual files. Then we create a microbatch scheduler, which is going to run every 5 seconds. And then we wait for that scheduler to finish in 100 years. It's kind of a little joke, sorry. Filling in the to-do, so this is what's actually going on. So the microbatch, which runs every 5 seconds. I wish I had a pointer. The first thing it's going to do is grab some messages from Kafka or whatever message bus you're running. They're going to return as a list of JSONs. And then we're going to create a file processing thread which just accepts the input, which is the file name. And then for each thread, we'll throw it onto the thread pool. And there's a queue there that'll allow us to handle situations where there were more files sent or grabbed than the thread pool has space for. And I will come back to that. There's an interesting play that you can do. But below that is the description of the class that's taking in the file name and the Spark context reference. And then because this is a multi-threaded driver, this is one of the secrets, you have to initialize the thread local instance of the Spark env. Because if you don't do that, when you try to write to HDFS, some of the threads will conflict with each other and bad things will happen. So that's one of the little secrets there. And then below that, we have that super oversimplistic data transformation. So I just wanted to include that there and show you the threading secret. So that's how you do multi-threaded drivers in this situation. Now going back up there, I'll just briefly mention that I haven't shown it here, but you can monitor the thread pool and say, oh, it's full. I don't need to pull from Kafka. Kafka's a good persistent data store. So this approach or pattern allows you to do that. So that's just a quick recommendation. I didn't have space on this slide. So now patterns for exception handling. This is within that thread. You definitely must wrap all of your data transformations in a try-catch. And this is overly simplistic. You want to have catch different types of exceptions. But the reason for this is that if any Spark job fails, you don't want to bring the driver down and have it sitting there just a zombie. So definitely encapsulate every data transformation like I'm doing here. Of course, there's other sources of error in my example, such as the get messages call or the parsing of the JSON. You definitely also have to include handling of that. But I hope this is a useful example for everybody, and I hope it wasn't boring information. So also do use map partitions, because that allows you to perform error handling on the worker nodes in case there's 2 lines in a file that went bad. You don't want to have the whole file be excluded. So definitely use that in your work. So now on to graceful shutdowns. This is something we've implemented to allow us to handle an application that's constantly getting files and might need to be brought down for maintenance. We run in Yarn, as I mentioned. If you're running in a standalone Java process, you don't submit to the cluster using Spark Submit. You can just write a Java shutdown hook. That's definitely available on the internet. But this lower section is an approach that we developed after talking to Cloudera, who helps us out with Yarn. And the suggestion is to write a JMX bean that accepts connections from a remote caller, allowing that caller to invoke certain methods, which can be essentially a shutdown hook. And then to make it easy for system administrators to call this, we've implemented using JMX term, which is a way of writing bash scripts that call Java methods. There are two secrets here. One is in red, that when you submit your driver application, you have to provide these Java options. And then below that is an example of how to create a shell script. So hopefully on the video, and if the slides go out on public, then you can look these up in more detail. I'm going to try to write a Cloudera blog post and possibly open source this as a Spark package. Here's more details. What's my timing? OK, I'm good. So this is sort of the implementation of that JMX bean. First 3 lines there are setting it up. So whenever you start your application, you want to create an instance of this class. And then if that Spark driver has those Java options, the ports, et cetera, will be open for calling. And then the run method here, I'm shutting down the batch scheduler, shutting down the fixed thread pool, missing some code about how to hold on those actions. You definitely want to include that. But essentially, once those complete, your files have finished processing, and it's safe to shut the application down, which I'm invoking this. It's kind of messy here, this thread, which allows the run method to return, and the remote end doesn't get an exception and unduly cause an error or concern. One other point that's important is right here, these options are disabling security features. You definitely must do this within a secure cluster where no one else will be able to access those ports. So that was it.
Thanks a lot. I am Dave, the first author. So in this talk, we are going to talk about 2 things. One is the similarity computation at large scale. And we have some more basically enhancement to matrix factorization on Spark. We are going to talk about that as well. So first, similarity computation. It is a very common code. We all know this. So in a map reduce flow, normally the column-based flow is most common. What do we have? We have a tall, skinny matrix. 60 million people, 100K items. Now, what do we do in map phase? Just give a partial score ij. And in the reduce phase, all you do is to sum them up, and that is your final score. Now, this has been checked in Spark 1.2. It's in row matrix.column similarities. Now, what we have is a row-based flow. This is the Jira that tracks this whole talk, basically all the things that I'm going to talk in this. So the column similarity, it has 2 particular use cases. One is if you don't have a tall, skinny matrix. What you have is a tall, wide matrix. What is wide? You have 1 million to 10 million items, which shows up very commonly in our advertising use cases. And the second use case is that you want to generate a kernel for a tall, skinny matrix. Means you want to find a tall cross tall matrix. And the common use cases are you have 60 million people, you ran a matrix factorization, found out latent factors, which is 50 to 400. Now you want to run a user cross user similarity. How do you do that? Now, one more use case which is very common is this devices. So we have a lot of device data that comes in. On that device, the features are dense, no longer sparse, features are less, maybe 100,000, that's it. Now on that device, you want to find out a 10M cross 10M matrix, basically. Now, this is the whole row-based flow that we added in Spark. There is a pre-processing step. The pre-processing step is that if you were handling a tall wide matrix, then you have to transpose the data matrix that comes in. The second flow is that if you have a kernel generation for tall skinny matrix, you don't do any transformation. You give the input to the data matrix. Now, in this, I'm just going to give you an outline. We have these few steps. In the algorithm, what we put together is a distributed matrix multiply, basically, and it makes use of a blocked Cartesian pattern. Means we block the matrices, then run Cartesian on top of that. We have two ways to control the shuffle space. So one is top k and one is a threshold number. So what is top k? Top k is very common. Normally you don't want to generate the whole tall cross tall matrix. All you need is top 50 or top 100 for every item, right? So that's one more. And by similarity threshold also, you can cut off the shuffle space. Now the third thing is that there is a distance function, right? Which is the for vector dot products, you can have many different distance function. So all what we support is cosine, Euclidean, RBF, and also scaled product. We'll come to that one soon. Few things on code optimization that we did. So one thing that differs from scikit-learn is kernel has something called the norms are cached in the kernel, so you don't regenerate the norms. So that way on distributed setting, it does help. So it will look a bit different from the scikit-learn kernel that most people know. Now, in Spark 1.4, we checked in the dense version of it. So the tall, dense vectors, right? That code you can see in Spark 1.4 recommend for all. It's in matrix factorization model. We have not yet found out a good place to keep it other than that. So this all, and for sparse vectors, we have a blast dot dot. And this particular check-in makes use of all of this code is in that particular pull request. But with Shangri and all, we are trying to get it broken into three different pull requests, and we are going to merge it soon. Now, here I'm showing you two kernel examples. We do make use of this in our flows. One is a cosine kernel, which you all know. So cosine kernel is very common when you are calculating item similarities. The only difference you will find is that norm is cached. So you can make use of the same norm, right, over and over. The second one, the scaled product kernel, goes into something called a content-based recommendation. Spark do have an alternating least square based flow. This one is a bit different. So this is trying to do a content-based, right? So we will go more details into this. But the whole point for you to show is that you can put your kernel function and rest of the code should run as it is. So you can define your own functions which you want to have your distance calculations. Now in this, we are showing you some runtime numbers, right? What we did, we took the known data sets. You all should know about these ones. So the ratings vary from 1M to 100M. Now the key thing is that on the right-hand chart, you will see there is a column and row flow. So even the column flow is running with similarity threshold of 1e minus 2. So what that does, it turns on a dim sum sampling. And that dim sum sampling is supposed to decrease the shuffle space. So we are comparing both the flows running with same similarity threshold. And the chart shows you the runtime of blue chart is the column flow, row chart, the green chart is the row flow. Now, why is this runtime coming from? The runtime is coming because of the shuffle space. We are optimizing on shuffle space much more. Now, I will go into next slide, more details. So we ran this code on our production. So we have some matrices, like one of the example is the 60M cross 2.5M. We could do it in around 4 hours with 1,000 cores for Spark. Now, this is the chart which says what is the reason for the runtime. I am not showing you the shuffle read chart. So if you see that chart, you will find that the shuffle read in row-based flow is really high. But because Spark can do very good job in block transfer, that runtime does not show up. In this, you can see the shuffle right runtime from, not runtime, the shuffle right space of row flow versus column flow. What we did, we optimized on the shuffle right, and that helps us in getting the runtime. Now, normally in column-based flow, you don't get a configuration called top K, but in row-based flow, you have the option to set up a top K, and in most of our use cases, we found that 50, 100 is fine. So that's, you only need 15 nearest neighbors and things like these. So that means that you can cut the shuffle space at 50 or 100, and you have never need to go to that row 1e minus 2. So that helps the runtime, basically. So that was part of my talk. I will take Dibendra to give a bit more detail on the recommendation part now.
Thanks, Deb. In my part, I will focus more on a particular application area. And this is really some kind of relative merits and demerits of two recommendation algorithms. These algorithms are probably known to many of you, but still some aspects might be relevant. We did some experiments on publicly available data sets. One data set is called the MovieLens data set, and the other one is the Netflix data set. And some metrics were measured, calculated. Mostly the KNN-based approach. I will focus on that one. And here, I compared it with the ALS-based implicit feedback formulation. When I say this, I need to point out the difference. The usual version that you see that deals with explicit ratings, but in real life, we rarely find explicit ratings. We usually find implicit ratings, whether an item is bought or not, or the amount of time some person has spent in watching a television program, something like that. Here, we converted the explicit rating to implicit rating and did our experiments. And the metrics we used to evaluate the recommendation algorithms are RMSE and precision at K. How we did the computation for the first algorithm, the KNN-based algorithm, it is captured by the above formula. Essentially, what we are doing, we are trying to predict one missing rating by a weighted average kind of a formula. We are considering all the items which are the neighbors of the ith item, which are similar to the ith item, and we are taking an weighted average. We are weighing each of these ratings by a similarity measure and normalizing it by the sum of the weights. This is actually the L1 norm of the similarity vector. You will find it in the denominator. And the way we compute it in code is as follows. The row similarities, similarity matrix dot row similarities, that one calculates, that one allows you to specify the number of neighbors you are using here. You may not use all the neighbors. That usually gives bad results. In fact, in my experiments, I found that something around 30 neighbors gave me very nice result. And Dev has already mentioned the row norms are cached. I used that feature also. And when I do this multiplication part actually, it comes in the second phase of the algorithm. There are two parts. In the first part, I compute the similarities. In the second part, I do the recommendation computation really. That will come in the next slide. Maybe, but even before that, let me introduce the other algorithm, the formulation of the other algorithm. This is the matrix factorization algorithm, and this is the ALS formulation. I should describe a bit the formula that is given there. The first factor 1 plus alpha times Rij, that gives us a notion of confidence. And the next term, that Pij term, that gives the value of preference. When Rij is positive, that preference assumes a value 1. When it is 0, it assumes a value of 0. It has a simple interpretation. And the next term, the Wi times Hj term, that corresponds to the matrix factorization terms. The next term, lambda times second norm of W plus second norm of H, that gives L2 norm, and that is the regularization term. In code, we use it, we specify that in the set user constraint line. Set user constraint smooth and set item constraint smooth, these two places. Okay, coming back to the comparison of these two algorithms, the KNN algorithm and ALS. In terms of the matrices, the metrics I described earlier, the RMSE term, the RMSE metric we computed, it shows that KNN did better compared to ALS. You see that RMSE values are low. We got lower error rates for KNN. But if you look at the next one, the precision at K value, you will find that matrix factorization always beats the KNN best algorithm. So what do we learn from this exercise? That is important. I should have included a conclusion slide, but I didn't. An ensemble of these two algorithms probably gives you the best answer. And also there could be another use case which is difficult to address by matrix factorization algorithm. That is the cold start problem. More specifically, if there is a cold item start, we cannot do much. But if there is a cold user start, we can start with a questionnaire. We can offer a questionnaire to the user, get his responses. And then KNN can enable us to give some recommendation for that cold user. But for matrix factorization, we cannot do that easily. We need to wait till the next time when the entire algorithm is run. So for online algorithms, KNN might be a better choice. That's all. Thank you.
Hi, good evening. Today I'll be talking about the segmentation results that we got from the ALS with constraints. So one of the data sets that we have is whenever a user clicks on a website, we get the time and the location information for some of the users, and then we have that as raw data, and then we can construct the zip code and website matrix. This is a sparse matrix that I've showed on the right-hand side. So this is contains like 30,000 zip codes, and our data sets here contains 30,000 zip codes and about 11,000 websites. And then the number of values there is like about 45 million ratings. And each value is the time unit feature that we extract from each location. So what we do is we take the sparse matrix that we constructed, and we run ALS with positive constraints, and the formulation is shown below here. So ALS output will give us two matrices. One is the zip code factors, and one is the website factors. So if you look at it, each row in that matrix is a website zip code factor, and each column there is a website factor. However, when you look at the columns of W transpose and then rows of age, what do we get? So it turns out that ALS with positive constraints will automatically segment the data, and we get some of the local and global clusters for both zip codes and websites. I'm going to show you the results in the next slide. So I'm sorry I cannot see this picture clearly, but what we get is some of the local features, local segments are shown in this map of on the map. So what we say is some of the segments um, that we get is concentrated on local areas on the map. That means the zip codes corresponding to the local areas. And then if you look at the websites corresponding to those segments, most of the websites that we get are local to that area. And we also get a couple of global segments. When I say global segments, the zip codes are distributed over over the entire map. And if you look at the websites corresponding to these global clusters, they are mostly like Google or Twitter or Pandora, which people can log in from any zip code. So we tried to plot all the local clusters on a map just to see how it looks. So it turns out that the ALS with positive constraints automatically comes up with these local clusters. And then I have to say at this point that we don't have any latitude or longitude information in this data set. It's purely zip codes and website information in the data matrix that we have. So that's basically what we have at this point. And also, we tried with several other constraints. So we have a code segment that shows that we are using positive constraints, and that's the way we give the positive constraint to the ALS algorithm. And we have some other constraints like simplex and L1 constraints. You can see all these things in this pull request that I've shown. Thank you.
Hello. Thank you for the good talk. So next we'll have the OnQ team to do the second half of the talk. Pass the ball to Joaquin.
Hello, folks. Well, OnQ is really a code name of a project that started at Intel that deals with the new generation of mobile and video and television streaming over the top. So that's a project that you may have heard in the news. Verizon bought OnQ, so the big project there came to Verizon, and there's a strategic project going on. But I want to talk about a little bit about, just to give you a glimpse, and also Diana will walk you through some of the interesting use cases that we've had and the problems we've had also working with Spark and how we've been able to tackle them. Now, I do have to give the pitch. So why to join? Well, first of all, we are a Scala shop. From scratch, OnQ started developing in Scala. And we love Scala developers. We hosted the Scala meetup here. We also pretty much work on different levels. So there's video and obviously audio processing groups. There's hardware group. My group in specifically, we're dealing with advertisement and recommendations. So a lot have to do with the talks that were previously given. One interesting thing is that we're finding a lot of similarities in the base of these two kind of pillars, the advertising pillars. We talked about segmentation, we kind of talked about recommendation engines, and obviously advertisers want to reach a given audience, and audience-based segmentation is key. So imagine now with Verizon, and obviously with the acquisition of AOL, all the data you would be able to get hold of. That's very interesting, right? And on the other hand, distributed systems, and of course, there's where our processing of that amount of data is, we're leveraging technologies such as Elasticsearch, such as Spark and Mesos. Today, we'll talk a little bit about the experience we have with Spark and Mesos. But we're hiring data scientists, or more importantly, engineers that want to be data scientists. And I'm saying this because we found that it's very different academically. I don't know if people have worked in trying to implement a paper and making it scale and work in reality. And a lot of it has to do with experimentation, so we're very keen in making sure that when we launch, we do A/B testing, we get the data, and we know what works, and data is king. And finally, we are a group that is contributing to the bottom line. So both engagement, and we're talking about a product. I can't talk much about the product, but it is a video, obviously a video application. And there's a lot that has to do with engagement, with virality, with viral communications and recommendations, social and promotions of products. So that, along with the advertising portion, which is the engine that powers the internet, right? Advertising is what powers right now, at least the business model behind the most successful internet business, is kind of the key here for why you would want to join the team. I will just pass it on to Diana. Again, if you want to reinvent or redefine how television works, or how video and television works for mobile and social, come and join us. Diana.
So as Joaquin mentioned, we are a full-on Scala shop, and that justified some of our reasoning why we decided to go to use Spark. And other of the nice things about Spark is a very nice framework to build data pipelines. And as a result of building data pipelines, there's all these operational details that we needed to go and figure out. So we have been developing on Spark since actually the version 1.0 actually. So that's quite a while back. Now we're already at 1.4 that was released, I think, a couple months ago during the Spark Summit. So this talk is a little bit about some of the lessons that we've learned throughout the process of developing different applications for advertising and recommendation systems. So very quick, I don't know how many people here know about Mesos, so I'm just going to give a quick introduction what Mesos is. So Mesos is a cluster management framework, which is open source. It was developed a while back by the folks actually as a research project from AmpLab in Berkeley. It was developed by Ben, the primary contributor was Ben Heinemann, who actually now runs Mesosphere, is part of Mesosphere. And funny enough, he collaborated with Matei. The very first technical paper that described Mesos as a framework came out, I think, in 2010. You can go and find it on the Berkeley website, and you can see Matei and Ben started developing all of these ideas. So a lot of some of the notation and naming kind of can be a little bit confusing in terms of when people talk about executors in Mesos and executives in Spark, they kind of use the same vocabulary. So some details on what Mesos does is a nice framework for resource sharing and also resource isolation. So these are two keywords, isolation and sharing. And what is interesting about that is that you can have in a given cluster run multiple applications at the same time while having a nice isolation in terms of your environment. And some of the ways they achieve that is they have this concept of every framework, a framework in Mesos implements two types of schedulers. There's a scheduler, and there's also the executor. And they communicate through this concept of offers. It can sound a little bit complex, but the nice thing about having offers from the Mesos master is that a framework scheduler can either accept or reject offers. And if they accept the offer in terms of offers of resources, then the executor then can run the job. So in this example, we have two kinds of frameworks running. You have a Hadoop scheduler and an MPI. So you can see that there's for Hadoop, there's a scheduler, and for MPI, there's a scheduler. And on the slaves, you see there's an executor for Hadoop and MPI. And on the third Mesos slave, you can see they're both sharing the same node. So the nice thing about this is that why it's nice to use Mesos is the next generation resource model. And part of that is that Mesos is implemented on top of the Linux C group, so that gives very fine-grained control of the kind of resources that a given framework can use. And in this case, for Spark, you could control the number of cores you can use in your cluster, the number, how much memory you use, even the file system, and I/O can be specifically tailored. So as a result of this, Mesos, why we chose Mesos, is that you can support applications beyond traditional Hadoop ecosystem, which is more on the Yarn side. So we can run our own services as well as running batch jobs and data analytics jobs in the same cluster. So it's a nice idea where you could have services that are running, let's say, constantly, and then at night when things are more quiet, you could schedule jobs that are heavy processing and make use of those resources. So in that sense, what Mesos look like is kind of like this. The analogy would be the OS for distributed system, where you can schedule jobs on top of it. So now a little bit on some of the downside of working with Mesos is it's so bleeding edge. It's a less mature ecosystem, so they're moving really fast. And we've been working with Mesosphere constantly, and we are always on the latest revision. So there's pros and cons. For example, there's certain bugs that we find, and then we work with Mesosphere, so on and so forth. So there's some of that, but I think as the industry moves forward, it will be more stable, and it's quite exciting to be at the bleeding edge of it. So now, a little bit on what it means to run Spark on Mesos. So the general idea of Spark, they have this nice abstraction where you have the Spark drivers and also the Spark executors. So all of the jobs in Spark have this concept of a cluster management abstraction. And the cluster management could either be a local instance of your Spark, so you just run your regular Spark jobs in your laptop, or it could be on Yarn, or it could be on Mesos, or it could be standalone. So in this case, our cluster management is Mesos. Some of those details that we learned along the way, this is one of the key insights we found, is the different modes we can run Spark on Mesos. So you can either run it as a coarse or a fine-grained mode. And what it means to run, there's trade-offs between using a coarse or a fine-grained, and it really depends on the type of application. So in terms of a coarse, why would you choose to run a coarse? So let me first actually explain what a coarse mode Spark application means. So it means that when you launch a Spark job, it runs as one executor of a long-running Spark job, and the tasks are spawned and controlled by Spark, not by Mesos. So in this sense, the Spark executor within this Mesos executor is agnostic to Mesos, so all the resources that are allocated are locked down. On the other hand, with a fine-grained mode, the Spark executors actually know about Mesos, so it launches one Mesos task per Mesos executor. And in this case, the tasks are spawned as threads. So there's pros and cons of why would you use a coarse versus fine-grained. So what we learned is that coarse grained is really good for tasks that need very low latency. And this could be for jobs that we already know the profile of how well they operate in terms of the data sizes that they need to manage. So this could be used for streaming applications that have a constant stream of data that doesn't spike up too much, and you know how much resources you need in terms of memory or cores. And you also need a lot of, you need the low latency because you need the quick response with Spark streaming. On the other hand, with a fine grain, you get better resource usage because as a result, you can have multiple Spark tasks that are spawned by Mesos. But the downside of that is that you have a slower startup of the tasks. And then this could be, in our case, what we found out is that it's a better use case for long-running batch jobs that we don't really care how long they take. I mean, it's kind of like a day, 2 days is fine. But I suppose for cores, we really care about the resources. So we want the most efficiency and have the tasks scheduled by Spark and not incur the overhead of the task serialization in the fine-grained mode. So other lessons that we learned is that in terms of resource allocations and scheduling is a very tricky fine line. You have to really understand your data set that you're dealing with to, let's say, I need 20 cores versus 5 cores and really understanding the application. So this comes with a lot of trial and error running our applications. And also understanding whether we want to run something via Kronos or via Marathon. And just the obvious case, easy use case is batch jobs in Spark. We run it through Kronos. And Kronos is a framework on top of Mesos that uses, it's kind of like cron jobs, but for Mesos. Then Marathon is for, people use it in Mesos for long-running services that are resilient. So if your service goes down, Marathon automatically launches it back. So in this case for Spark, we can use it for Spark streaming applications so that if you have a long-running Spark streaming job that constantly consumes data, we would run it on Marathon. So that if for some reason there's some error and then Spark driver for the streaming job goes down, then Marathon automatically can launch it back so we don't have a lot of downtime. So it's all automated. Other lessons we have been having that we're still kind of working on is having some issues on, this is not necessarily for Spark, but some issues that we have right now on HDFS. But I think some of these are going to be solved in the future if we run HDFS as a framework on top of Mesos. Some of the biggest wins and details and tweaks that we found are also tweaking some of these Spark configurations that run on to play nice with Mesos in a sense. In particular, and this is because we're not running Spark on Docker and other details that if you have a job in Spark that is running on Mesos and it crashes, it doesn't all the time automatically clean up its Scratch directory. So it was important for us to predefine the Spark local directory to a location, to a path in Mesos, which would automatically clean up inside the framework in Mesos. I don't know if that makes sense. Otherwise, the disk kept getting full because it didn't get cleaned up. Same thing with the event log directory, and other details that we tuned up in our applications were handling turning on some of the features that they had in the later releases of Spark, which is in particular enabling the Spark shuffle to spill onto disk. Also consolidating the shuffle, because shuffle is very expensive, is when all of your tasks in Spark distribute and they need to do a reduction. Other configurations were also the Spark RED compression, which was although we maybe as a trade-off, for compressing our data, we have to incur more CPU cycles, but it reduces a lot of the serialization that we have to do. Also, Spark Cleaner time to live was another one that we had to tweak a little bit for our Spark streaming applications. So now future work or ongoing work is to try Spark on Docker, which will solve some of these issues actually. A lot of the issues that we have with Spark not cleaning up after itself would be solved through Docker, but on the other hand, you have other side effects on Docker. And these are more specific to Mesos than Spark is running HDFS as a framework and Kafka as a framework on Mesos. So I think that's it.